Welcome to the deep dive. Sometimes you just wish you had a shortcut, right?
Yeah,
A way to really get the core ideas from complex stuff without wading through everything.
exactly.
Well, that's what we do here. We take dense material, find the absolute gold, and give it to you, crisp and clear. It's about getting you that well-informed edge fast. Today, we're digging into the world of C programming. Our guide is the book C Programming Language from Knowledge Flow Books.
A classic topic.
Yeah. So whether you're prepping for a meeting, just curious, or maybe catching up, this is for you to really grasp C's fundamentals quickly and thoroughly.
And C, well, it's not just any language. It's incredibly flexible, powerful, a real general-purpose workhorse.
Yeah.
It all started with Dennis Ritchie at AT&T Bell Labs way back early 70s, though roots go to 69.
Right, Bell Labs. Huge history there.
Immense. And it just took off, became super widely used, and amazingly, it still is, especially in things like embedded systems.
Okay, let's unpack that. Why is C, something from, 50 years ago, still so critical, especially for operating systems, embedded stuff? It feels like more than just features.
It really is. It's about control. See, a lot of modern languages, they kind of hide the machine from you.
Extract it away. Yeah.
Exactly. C doesn't do that. It gives you direct memory access. You can talk right to the hardware, almost.
Ah, okay.
And that fundamental difference. That's why C can be blazing fast and super efficient with resources.
Which is key for those embedded systems like in cars or phones.
Absolutely critical. Your car's engine controller, the firmware in your phone, the core of Windows or Linux, tons of C under the hood. It forces you to learn how computers actually work. Plus, technically, it's a high-level compiler language.
High level,
Yeah,
but also gives low-level control. That sounds a bit contradictory.
it does, doesn't it? High level here means it's easier for humans to write than raw machine code. It has structures, functions, things that make sense to us. But it compiles down very efficiently.
Okay, so compiler language. What's the big deal there? How's that different from, say, languages that are interpreted?
Ah, good question. It's a key difference. Think of an interpreter like a live translator at the UN, doing it line by line as you speak.
Okay, yeah.
A compiler is more like translating an entire book into another language before anyone reads it. It takes your whole C source code file.
All the instructions you wrote.
Right, and translates it all at once into machine code.
Yeah.
The actual instructions the computer's processor understands.
And because the translation is done up front.
The execution is incredibly fast, no translation happening on the fly. That's vital for performance-critical stuff.
Got it. That makes sense. Okay, so context established. Now, if you actually want to write some C, where do you start? The absolute basics.
The very alphabet, really. We call them character sets. These are literally all the characters C understands and uses to build everything else.
Like letters and numbers.
Yeah. Exactly. You've got uppercase A to Z, lowercase a to Z, digits 0 to 9, and then a bunch of special symbols like plus, minus, parentheses, curly braces, all that.
Okay.
Every single instruction, every piece of code is made from these characters. And crucially, each one has a specific numerical value behind it, an ASCII code.
ASCII.
Yeah, it's a standard. It's how the computer actually represents a or even a space internally as a number. So it can process and, calculate with them if needed.
Okay, so we have the letters. How do they form actual words or commands the compiler understands?
That's the next step. C, tokens. If characters are letters, tokens are like the words and punctuation. They're the smallest individual units that have meaning to the compiler.
Makes sense.
And they mainly fall into two groups. Keywords and constants.
Keywords, like special reserved words.
Precisely. Words like if, else, while, int, float, char. C reserves these. They have a built-in meaning, and you absolutely cannot use them as, say, variable names.
Got it. So they're protected words. What about constants?
Constants are values you define in your code that, stay constant. They don't change while the program is running.
Like the number pi or something?
Could be. There are different types. Numeric constants, those are your numbers. They can be integers, like 10 or -5, no decimal point, or real numbers like 3.14 or -15, which do have a decimal point.
Okay. Integers and reals.
Then you have character constants. Just a single character written inside single quotes, like A or dog.
Cool quotes for single characters. Right.
And finally, string constants. These are sequences of characters, like a name or a message enclosed in double quotes, like hello world.
Double quotes for strings. Got it. You mentioned an example earlier. Char5 used John. That looks like storing a string.
It is. That declares a character array named A. The 5 means it reserves space for 5 characters.
But John only has 4 letters. Why 5?
Excellent question. That leads to a really important detail about strings in C. When you store a string like John, C automatically adds an extra invisible character at the very end.
Invisible.
Yeah, it's called the null character. It's written as 0. It basically acts as a stop sign, telling functions, okay, the string ends here.
So the array needs space for the letters plus that null character.
Exactly. So an array declared with size n can hold a string of n1 actual characters plus the null terminator. It's crucial for making sure functions know where the string ends.
That's a key detail.
Yeah.
Okay, so we have characters, tokens, keywords, constants. Now, what about storing information that can change, like user input or results of calculations?
Right. For that, we need variables. Think of them as named storage boxes in the computer's memory. You give a box a name, and you can put data into it, change it later.
But it's temporary.
Generally, yes. For variables declared inside functions like main, their contents are usually lost when the program finishes. They hold temporary values during execution.
And naming these boxes, these variables, are there rules?
Oh, yes. Variable names can use letters, upper or lowercase, numbers, and the underscore character. But the first character absolutely must be a letter or an underscore. It cannot be a number.
Yeah.
And no blank spaces allowed in the name.
Right, no spaces. Underscores are okay, though.
Underscores are fine, often used to separate words like user input or totalsum.
So before I use a variable, I have to declare it. Tell the computer about it first.
You absolutely have to. It's like booking a storage box before you use it. In C, you typically declare your variables right at the beginning of a function block, usually after the opening curly brace of void main.
And when I declare it, I give it a name.
A unique name, following the rules we just mentioned. And crucially, you must also tell the compiler what kind of data that variable is going to hold.
Like whether it's a number or a character.
Exactly. This is done using data types. Data types define two things: the type of data, integer, character, real number, and how much memory space should be set aside for it.
Okay, so what are the main data types in C?
There are 4 fundamental ones you'll use all the time. First is char.
For characters, presumably?
Yep. Single letters, symbols, things like a day. There are variations like signed char, unsigned char, but char is the basic one. Usually takes up 1 byte of memory.
Okay, char. What's next?
Int. This is for integers, whole numbers, positive or negative, no decimal points, like 10, 0, negative 2500.
How big can an int be?
Typically, on many systems, it ranges from around negative to 32,768 to plus 32,767. You also have variations like short int, potentially smaller range, and long int, potentially larger range.
Got it. Char for characters, int for whole numbers. What about numbers with decimals?
For that, you have float. It stands for floating point, used for real numbers that have a fractional part, like 3.14159 or -, 0.05.
And the range for float?
It's quite large, something like plus or minus 3.4 times 10 to the power of 38. Gives you a lot of precision, but for even larger real numbers or higher precision, C provides double. Think of it as double precision floating point.
Bigger range, more precise.
Exactly. The range is enormous, something like 1.7 times 10 to the minus 308 up to 1.7 times 10 to the plus 308.
Yeah.
Takes up more memory than float, usually 8 bytes compared to 4 for float, but necessary for certain calculations.
Okay, so char, int, float, double. Those are the core 4.
Those are your workhorses, yes.
All right, so we know the characters, the words, tokens, how to store temporary info, variables, and what kind of info, data types. But how do we actually, talk to the program, get info in from the user, or display results out?
Good question.
Yeah.
That brings us to input-output functions, often called I/O functions. They handle the communication between your program and the outside world, usually the user's keyboard and screen.
Okay, so how do I get input if I want the user to type something?
For that, the standard function is scanf, and it stands for scan formatted.
Scan formatted?
Yeah, its job is to read input from the keyboard and store it into variables according to a specific format you provide.
How does that work, syntax-wise?
The basic syntax looks something like this: scan, control string, and variable name.
Okay, and variable name. What's the ampersand at for?
That's crucial. The endian gives scanf the memory address of the variable. Remember pointers. Scanf needs to know where in memory to put the value it reads. So you give it the address of the variable, not just its name.
Got it. Address of the variable. And the control string.
The control string tells scanf what type of data to expect. It uses code starting with a percentage sign %.
Like
%d for reading an integer, d for decimal integer, %way for reading a float, % for reading a single character, and % for reading a string.
So I need to match the control string code to the type of variable I'm reading into.
Absolutely. If you try to read an integer using percent or float using percent, you'll get garbage or unexpected results. The type must match.
Makes sense. So scamp is for input. What about output, displaying things on the screen?
For output, the standard function is printf. Stands for print formatted.
Print formatted. Okay.
It's really versatile. You can use it in a couple of main ways. Simplest is just printing a message. Printf.
Hello world in it.
And the N at the end, that's a special character sequence representing a new line. It tells printf to move the cursor down to the next line after printing hello world, keeps your output neat.
Okay, so simple messages. What else can printf do?
The powerful part is printing messages along with the values stored in your variables. The syntax is like printf, message a control string, variablist.
Control strings again, like percent and percent.
Exactly the same ones. You embed them in your message string where you want a variable's value to appear. For example, printf, the sum is Bing and total. If total holds the value 50, that line will print the sum is 50, followed by a new line.
And I can print multiple variables.
Yep. Just include multiple control strings in the message and list the corresponding variables afterwards in the correct order, like print value 1%, value 2%, and count average.
Very cool. So scan for input, print for output. That covers basic interaction. But you mentioned C is used a lot with systems. Does it handle files on the disk too?
Oh, definitely. Interacting with files is a core capability. C provides specific functions for reading from and writing data to files stored on your computer's disk.
How does that work? Is it similar to scamped and printf?
There are file-specific functions, but also some that look quite similar. Let's break it down. For basic text file operations, character by character, you have puttrcup and gettrcup. Puttrcup writes a single character to a file. Gettrcup reads or gets a single character from a file.
Okay, character by character.
You also have puttruck and get, which do the same thing, but for integer values. W for word, historically, getprut writes an integer. Gettwood reads one.
And these need, like, a way to know which file to use.
Exactly. They all operate using something called a file pointer. Before you use these functions, you have to open the file, which gives you back this pointer. You also need to specify the mode, like read mode R if you're using getter, or write mode W for puttruck or put2.
Right. Makes sense. You need permission and the right connection.
Precisely. But here's where it gets interesting. There are two other functions, fprint and fscanf, that are incredibly versatile.
Fprint and fscanf. Like print and scanf, but with an F?
Kind of. The F stands for file. These functions work almost identically to print and scanf using control strings like part50%, mentor%, but instead of always going to the screen or keyboard.
They can go to a file.
Exactly. You just give them a file pointer as the first argument. So fprint, my file pointer, data to the end value, writes formatted data to the file pointed to by my file pointer.
And fscanf reads formatted data from the file.
Fscanf, my file pointer, tar_city, %enum, and price, reads an integer and a float from the file.
Okay, that's powerful. So they work like their screen keyboard counterparts, but for files.
But wait, there's more. They can also be used for the screen and keyboard if you want. C has predefined file pointers for standard input, stead in your keyboard, and standard output, stead out your screen.
So fprint to zout is basically the same as printf.
Pretty much identical in effect, yeah. And scant is essentially the same as scamp. It just shows their underlying connection to the file I/O system. Very flexible functions.
Wow, okay. That's a lot packed into I/O. So we can get data in, process it, store it, send it out. But programs aren't usually just a straight sequence of commands, right? They need to make decisions, repeat things.
Absolutely. A program that just runs top to bottom isn't very useful most of the time. You need ways to change the flow of execution. That's where control structures come in.
Control structures.
These are statements that let your program make decisions or repeat blocks of code based on certain conditions. They control the sequence. There are three main types.
What's the first type?
Selection statements. These let the program choose between different paths. The most common are the if statement and the if-else statement.
If this condition is true, then do this.
Exactly. If condition, code to run if true. You can add an else part, code if true, a code if false. It lets your program react differently based on circumstances.
Simple enough. Makes sense. What's the second category?
Iteration statements. You probably know them as loops.
Loops, right, for repeating things.
Precisely. Their job is to execute a block of code multiple times. C gives you three main types: the for loop, the while loop, and the do while loop.
For while, do while, are they very different?
They all achieve repetition, but they structure it differently. The for loop is often used when you know roughly how many times you want to repeat something. The while loop repeats as long as the condition remains true. checking the condition before each iteration. The do-while loop is similar to while, but it guarantees the code block runs at least once because it checks the condition after the iteration.
Subtle difference on the do-while. Okay, so selection for choices, iteration for loops. What's the third type?
Jump statements. These let you abruptly change the flow of execution, jumping somewhere else. The main ones are go to, break, and continue.
Go to sounds powerful, maybe dangerous.
It can be. Go to lets you jump unconditionally to another labeled point in your code. It's generally discouraged in modern programming because it can make code really hard to follow and debug. Spaghetti code, they call it.
Right. Avoid go to if possible. What about break and continue?
Those are much more common and useful, especially with loops. Break lets you exit a loop or a switch statement immediately, regardless of the loop's condition.
Just jump out completely.
Yep. And continue skips the rest of the current iterations of loop and jumps straight to the beginning of the next iteration. Useful if you want to bypass processing for certain items in a loop.
Okay. Break out, continue to the next round.
Yep.
Got it. So control structures give the program logic and flow. Now, we talked about char for single characters, but real-world data is often text, names, sentences.
Right. We deal with strings of characters.
Strings. How does C handle those? You mentioned character arrays earlier.
That's exactly it. In C, a string is fundamentally treated as an array of characters.
Char array.
For char. Could hold a name. Yes, it reserves space for 19 characters, plus that all-important null terminator, 0 at the end.
Always the null terminator.
Always for strings. Even though it's an array, functions like scanf with percents or print with percents know how to treat it as a single string entity, often handling the null terminator automatically. You don't always need a loop just to process a string character by character, although you can if you need to.
And if I need to store, say, a list of names?
Then you typically use a 2D character array, like char names 120, that would reserve space for 10 names, each up to 19 characters long, plus the null.
Okay, an array of arrays. Makes sense. What about doing things with strings, like copying one string to another or joining them, say, first name and last name?
String manipulation. C provides a whole set of helpful functions for this, but you need to include a special header file first, string.h.
String.h. Okay. What functions does it give us?
Some really common ones. For copying a string, there's strcpy. Stands for string copy. Syntax is like strcpy, destination, source. It copies a source string into the destination array.
Important. The destination array needs to be big enough, right?
Absolutely critical.
Yeah.
Strcpy doesn't check. If the destination isn't big enough, you'll overwrite memory, causing bugs or crashes.
Okay, be careful with strcpy. What about joining strings? Concatenating them.
For that, you use stropit. String concatenation, strcat, destination, source, appends the source string onto the end of the destination string.
And again, the destination must be large enough.
Even more so here.
Yeah.
It needs space for its original content, plus the content of the source string, plus the final null terminator.
Gotcha. Handle with care. Any other key string functions?
One more you'll use constantly is stroply. Strunglen. Strunglen my string tells you how many characters are in my string, not counting the null terminator.
Useful for checking sizes before copying or concatenating.
Exactly. Or just knowing the length for other processing. These library functions are super useful and generally very efficient.
Okay, strings handled. Now, as programs get larger, just having one long main function seems like it would get messy fast.
Oh, incredibly messy. And hard to manage or reuse code. That's why C heavily relies on functions.
Functions, like self-contained blocks of code.
Precisely. Think of them as mini programs or modules within your larger program. You define a specific task inside a function, maybe calculating an average, sorting data, printing a menu, and then you can call that function whenever you need that task performed.
So you write the code once, use it many times?
That's the core idea. It promotes code reuse, makes programs easier to organize, debug, and understand. You break down a big problem into smaller, manageable, function-sized pieces. The main function itself is just a special function where the program execution begins.
Are there different kinds of functions?
Broadly, yes. You have library functions, which are the pre-built ones C provides, like print, scamp, stripey, stripeln. They come with a compiler.
The ones we've been talking about.
Right. And then you have user-defined functions, which are the ones you write yourself to perform specific tasks for your program.
Okay, so I can create my own reusable blocks. What are the essential components when I define my own function?
Every function you define has three main parts you need to specify. First, the arguments, sometimes called parameters.
The data the function works on.
Exactly. The input values the function needs to do its job. A function can take 0 arguments, one or multiple arguments, and they can be of different data types.
Okay, arguments are the input. What else?
Second, the return type. This specifies the data type of the value that the function will send back to the part of the program that called it after it finishes its task.
So if a function calculates a sum, the return type might be int.
Perfect example. If it calculates an average, it might return a float or double. If a function doesn't need to return any value, its return type is void.
Void for no return value.
Got it. And the third part?
The function name. Just like variables, you give your function a unique name so you can call it. Same naming rules apply: letters, numbers, underscore, start with letter or underscore, no spaces.
Okay, so return type, function name, and arguments in parentheses, like int, sum, int, a, and b. Exactly like that. That declares a function named sum that takes two integer arguments, a and b, and is expected to return an integer result. Then inside curly braces, you'd write the code that actually performs the addition and returns the result.
That structure seems much cleaner for larger projects.
Immensely so. It's fundamental to structured programming in C.
Okay, now, there's a concept in C that often seems a bit intimidating but also really powerful. Pointers. We touched on them with scanf needing the address. Can we dig into pointers a bit more?
Absolutely. Pointers are, well, they're arguably what gives C much of its unique power and reputation. They can be tricky at first, but they're essential.
So what is a pointer, fundamentally?
Okay, think back to variables as named boxes holding values. A pointer is a special kind of variable, but instead of holding a regular value like 10 or a,
Yes.
it holds a memory address. It holds the location where another variable is stored in the computer's memory. It literally points to that other variable's location.
So it doesn't hold the data itself, just where to find it.
Exactly. It's like having a piece of paper with the house number and street name, rather than having the actual house.
Why is that useful? Why not just use the variable directly?
Several reasons. It allows for very efficient ways to pass large amounts of data to functions without copying everything. It's fundamental for dynamic memory allocation, creating variables on the fly while the program runs. And it's essential for building complex data structures like linked lists or trees where elements need to point to each other. Plus, it allows direct manipulation of hardware memory locations, which is crucial for systems programming.
Direct memory manipulation. That sounds powerful, but also maybe risky?
Very much so. This is the double-edged sword of C. Pointers give you incredible power and control, letting you get very close to the hardware. But you make a mistake with a pointer, point it to the wrong address, use it after the memory it points to is gone, you can cause serious problems. Crashing the program, corrupting data, security vulnerabilities. C trusts you, the programmer, to manage pointers correctly. It doesn't provide as many safety nets as some newer languages.
So, great power, great responsibility.
That sums it up perfectly for C pointers. Understanding them well is key to mastering C.
Okay. Let's shift gears slightly to another advanced topic, recursion. What's that about?
Recursion is a programming technique where a function actually calls itself from within its own definition.
A function calls itself. How does that even work? Doesn't it just loop forever?
It could loop forever if you're not careful. The key to making recursion work is having a base case, a condition within the function that stops the recursion. When the base case is met, the function stops calling itself and starts returning values back up the chain of calls.
So it's like nested calls until it hits a stop condition.
Exactly. Think of calculating a factorial, like 5. 5, 4, 3, 2, 1. You can define factorial n as n factorial n.
It relies on the result of calling itself with a smaller number.
Right. And the base case is factorial, which is just 1. So factorial 5 calls factorial 4, which calls factorial 3, and so on, until it hits factorial 1. Then the results multiply back up the chain. 1, then 21, then 32, then 46, then 524, giving 120.
Okay, I can see how that works. Is it just an alternative to loops, then?
In many cases, yes. Anything you could do with recursion, you can usually do with iteration loops, and vice versa. Sometimes recursion leads to more elegant, easier to understand code, especially for problems that are naturally recursive, like traversing tree structures. But it's not always the most efficient way each function call uses memory on the stack. So deep recursion can sometimes lead to Stack Overflow errors. It's another tool in the toolbox.
Good to know. Elegant, but use with care. Okay, last major area. Things going wrong. Error handling. Especially with files, you mentioned things can fail.
Yes, robust programs need to anticipate and handle errors gracefully. With file operations in C, there are several common pitfalls.
Like what?
Well, the most basic is trying to open a file that doesn't exist, or maybe you don't have permission to read or write it. The fopen function, which you use to open files, will return a special null pointer, NULL, in these cases.
So you have to check the result of FOPN?
Absolutely. Always check if the file pointer is NULL immediately after calling FOPN. If it is, print an error message and probably exit the program or handle it appropriately. Don't try to use a NULL pointer with fscanf, fprint, etc. that will crash your program.
Okay, check FOPN. What else?
Trying to read from a file opened only for writing, or write to one opened only for reading, using an invalid mode string in FOPN, or a common one when reading data, is trying to read past the end of the file.
Reading past the end, how do you detect that?
C provides a specific function for this, FIF. It stands for file end of file.
FIF.
You give it a file pointer, like FIF, my file pointer. It returns 0, which means false in C logic, as long as you haven't reached the end of the file. As soon as you attempt a read operation that goes past the very last bit of data, FIF will start returning a non-zero value.
True. So I can use that in a loop condition?
Exactly. A common pattern is something like, while that FIA. Try to read data.
Right.
This means, while it's not the end of the file, keep reading. It helps prevent errors from trying to read data that isn't there.
Checking FOPN return value using FIF. These seem critical for reliable file handling.
They are absolutely essential for writing robust C programs that deal with files. Ignoring error checking is a recipe for crashes and unpredictable behavior.
Wow. Okay, what a journey. We've gone from the absolute basics, C's origins, character sets, tokens, variables, data types,
right through to how programs interact using I/O functions like print, scan, sprint, fscanf.
and how to control the program's flow with if, else, for, while, break, continue.
Then into handling text with strings and character arrays, using those helpful string edge functions.
Structuring code with user-defined functions, understanding the power and peril of pointers.
Touching on recursion as an alternative way to loop. And finally, the crucial importance of error handling, especially with files using FIF.
It really provides a comprehensive map, doesn't it? From the atoms up to complex structures.
It really does. These are the fundamental building blocks and concepts you absolutely need to get started and build meaningful things in C.
So for you listening, having this overview, this mental map, is hopefully that shortcut we talked about, a way to structure your understanding of this incredibly influential language.
And it makes you think, C is over 50 years old, yet it's still powering so much critical infrastructure, operating systems, embedded devices. What does that longevity tell us?
Good question.
What fundamental computing principles does C embody so well that it remains relevant? And maybe more importantly for someone learning today, how might understanding a foundational language like C give you a unique perspective, maybe even an edge, in a tech world obsessed with the newest framework or language? What deep understanding do you gain by grappling with concepts like pointers and manual memory management that higher-level languages hide from you?
That's definitely something to mull over, how these core ideas persist and why understanding them still matters deeply, even today. Thanks for joining us on this deep dive into C.